So this is one of our identities here. If you want to calculate the value of G on Earth or the moon or a moon or any planet for that matter, you need the mass of the object and you need the radius of the object. And that's the radius from the center of the sphere to the surface, if you think of it like that. We calculated G on the surface of our planet to 3 decimal places. Justin, would you shut that door for me, please? Thank you. Yeah, mate. Yep. Okay, so today with a satellite in a circular orbit. Now, so one thing that's important is all satellites, well, there is no satellite that is the same. Lots of them share orbits or similar orbits. And when I say similar orbits, I mean they have a similar altitude, sorry. Yeah, similar on the scale of space. Yeah, that's right. And I draw these satellites as like a drum with an antenna on it. Okay, they don't look like that. You'll see what they look like shortly in the videos. And they can orbit at different altitudes, whatever this altitude may be, and there's different reasons for why we might choose a specific altitude. So the force that this satellite or whatever body it is, it could be you orbiting the Earth or the space shuttle or something like that. We all experience the same force. Capital M sub E is the mass of the Earth. That's you or the satellite, the little m, over r squared. We know that already. That's Newton's law of universal gravitation. The satellite or the orbiting body has a force associated with it. We call that the centripetal force because it's in uniform circular motion. Is equal to what? Can anybody remember? MA, of course, which is equal to mv squared over r. Okay. So we know that this is, I'll put this in a different color. This is the force all objects experience. And this here is the force that objects in UCM, uniform circular motion experience. Now, because these are one and the same at the moment, we can equate those. G, mass of the Earth, mass of the satellite over the radius squared is equal to the mass of the satellite times its velocity squared over r. There's some cancellations that we can do here. What am I aiming for? I'm aiming for this velocity, to find what this velocity is going to be equal to. So if I move this over there, then we can cancel one of those r's. Cancel it in orange. Cancel that, cancel that, cancel that, and cancel that. We're left with V is equal to the square root of So the velocity of the satellite in a circular orbit undergoing uniform circular motion is dependent upon the mass of the Earth and the radius at which they orbit. So really, if you're thinking about a satellite in Earth orbit, we're only looking at the radius at their altitude. So their velocity depends on their altitude. And I'll say that. Velocity when I say dependent upon, I don't mean proportional to, of course. Dependent upon. And in the last lesson I stated this. I said that this radius or altitude period of rotation. What's a formula for the period of rotation? Capital T for period. Period of rotation is the time it takes in seconds to travel to do one full oscillation, isn't it? And one full oscillation is one orbit around the Earth, one full orbit around the Earth. You'll remember this as soon as I say it. 2 pi r on V. From that, we can say that V is equal to 2 pi r on the period. And we also have, from before, we have this V is equal to the square root of G ME on R. So from that I can say, from that V squared equals G ME M sub E, that is, on R. And V squared is also equal to, from this, yeah, V squared equals 4 times pi squared R squared over T squared. If I then equate those two V squareds, G ME on R. Stop me if you're not following. Pi squared on R, pi squared R squared on T squared. Let's move this stuff around. I'll do it in one step. T, well actually I'll leave it as T squared equals 4 pi squared R cubed on capital G M sub E. Period of rotation. That's something that you'll use also. Question? Kepler's laws? I'm not sure actually, to tell you the truth. Is it? Yeah, do you know anything more about it other than that? Yeah, to tell you the truth, I don't know about Kepler's laws. So I know of Kepler, but I couldn't tell you how he relates to this equation here with regard to the period. Okay. Is there a problem here? Yes, there is. Let me open this problem page. Question? What's the matter? Someone at the door? Yeah, ask them in. You guys can do that, I think. Hello. Ah. Here's a problem for you guys to do. I don't think this one is particularly difficult. Have a go at it though. It's good for you guys to practice these problems. That's right. Capital G, I'll put this up here, 6.67 by 10 to the minus 11. B equals, this is one way to do it, there's another way. GME, I'm going to state my formula first, the formula that I'm using on R. It is in seconds, yes, SI units for physics are seconds. .67 by 10 to the minus 11 times the mass of the Earth, 5.977, 10 to the 24 kilograms. Quite massive. On R. A question? I beg your pardon. So, is it? Yeah. Okay. So this here, we've just been informed, is Kepler's third law of planetary motion. Ah, okay. Kepler's. That's good. Yeah, I didn't know that. There it is, deriving something that I didn't know what the name of it was. Again, V equals 1.0186 by 10 to the 3 meters per second. So a thousand meters per second, a kilometer per second. Then I'm going to go to this. You guys could have gone straight to your Kepler's third law of planetary motion. 2 pi r on our little v. Two times pi times r, which is 3.844 10 to the 8. Yeah, everybody's going to be inclined to use this Kepler's law of planetary motion. I'm just doing it a different way to show you that it works out the same. 1.0186 by 10 to the 3. 2.3712 by 10 to the 6 seconds. Does everybody concur with that value there in seconds? Now, they want the answer in days, don't they? So that's seconds. What do I do to this number? Answer divided by 60 times 60. So 60 seconds in a minute, 60 minutes in an hour, by 24 hours will give us a day. $27.4 days. I hope you got that. Both of these work. This and Kepler's third law of planetary motion work the same. You should get exactly the same number. That's that problem there. Ah, okay. This is our application for this topic. Now, I'll just show you a brief idea of what's going on in space around the space around the Earth very quickly, and then we'll go to a video. This is Earth, of course, and we know that there's satellites orbiting the Earth. They can orbit in different directions. Okay, these are possible orbits. Why are they possible orbits? Please. Possible orbits. This question comes up a lot in the exam, in the test and the exam. Actually, I'll say the center of their circular orbit coincides with the center of the Earth. Center of the Earth in here somewhere. I'll show you an impossible orbit. That's not possible. That's not possible. The center of the circular orbits here are somewhere, they're in there somewhere. They don't coincide with this point here. They must coincide with that center. Otherwise, what happens? Well, for this orbit here, for this object in uniform circular motion, it's not going to be maintained, is it? Because this force, the force that's causing it to go towards this center here, that force is not constant. Yeah, the force that is constant is actually, yeah, towards the center of the Earth, isn't it? It's down. So what's going to happen over time is, well, over a very short amount of time, immediately, in fact, or near immediately, not quite immediately, but very close to, uh, is this satellite's orbit is going to be pulled down towards the center of the Earth, and of course, then it's not going to continue in orbit. It would need engines to maintain that, constantly firing. Let's go to a video. And you're standing on the Earth somewhere. Say at this point, right here, and the sun goes below the horizon. So here's the sun, and the sun for you, of course, is below the horizon. Uh, what's still happening with the sun is, of course, it's sending rays off in this direction. And what's good at this time of night is you might see, if there's a weather or communication satellite in the sky, it's lit up by the sun's rays at that point, and you can see it. Okay, so that's a good time to look for satellites at night. Of course, the geostationary satellites, with their very high altitude, you won't be able to see them. Why is that? Yes, they're too far away and too small, but also, a big pardon? Light pollution, yes, definitely. But also, even if you could see them, they'd look like a star because they stay above the same point on the Earth, so they don't appear to move. If you take a time shot of the sky, you'll see the stars moving in a circular pattern, and that star will appear to stay still. So yeah, that's a geostationary satellite. That's the first one that we look at, geostationary satellite. Geostationary satellites orbit above the same point on the Earth. They have a period of 24 hours. Now, if you remember, V equals square root of m sub e, g m sub e on r. If this radius is very large, then this velocity can be very small. And so geostationary satellites, they said in that video that this distance here, this altitude is about 36,000 kilometers. Approximately. So let's look at that. T equals 24 hours, which equals 24 by 60 by 60. 24 hours times 60 minutes in an hour times 60 seconds in an hour. 60 seconds in a minute, beg your pardon. 8.64 by 10 to the 4 seconds is the period that we want this to have. Okay, this satellite, we want it to stay above the same point on the Earth and have a period of 24 hours. Notice also that the Earth is rotating. If this is how I always remember. Don't laugh at my Australia. Okay, so where does the sun rise? Rises in the east, doesn't it? So in which direction is the Earth rotating? Anti-clockwise from the yes. Okay, so if you look at it, it's actually rotating in this direction because the sun will rise on the east side of Australia, and so it's west to east. The Earth rotates in a west to east direction. That's important. From our formula before, we had this. T squared equals 4. Tell me if I'm wrong. Yes. R cubed, yep. Well, we'll finish this next lesson.